So before we dive in, were there any questions on the material previous? We just did the Cahoots that reviewed a few things. The main thing or reason I wanted to emphasize the radiochemistry part of chemistry is because I think that we're going to have to use nuclear power in the future. I think, and it's good for y'all to have some understanding of how we've used it in the past and that we're using it in the present. A lot of people will talk about the success story in Central Europe of France and Germany using nuclear power, and they say France uses 80% of its electricity is generated by nuclear. And they saw an incredible improvement in their air quality because it's so densely populated in Europe with coal-fired power plants, even worse in the past before they scrubbed the stacks. The black smoke coming out of those stacks that was not only for electrical generation, but just their power, the steam, basically the Industrial Revolution was all based on coal and steam power. And this unburned coal soot would just go all over. You can look at all the cathedrals from back in those days and they're just black. The stone would just collect all of that soot. Things improved greatly when we started scrubbing those stacks, but then improved even more when they went to nuclear and quit having basically a lot of flue gases being released. Now, yes, so it makes it sound with 80% of their power generation being nuclear that France was the leader in nuclear energy, but we were actually in terms of the number of megajoules or megawatts of electrical power produced by nuclear. So I think we produce about twice the amount that France does. It's just not a larger percentage here. So on a percentage basis, France was top dog, but in terms of amount of power generated, we have a lot more nuclear power plants in this country. And so we've safely used it for decades. So that's great, but what about our health risks? Is this putting us at risk? So that's what this lecture is about, because I know that's a natural question. We're not going to just talk about the benefits. Let's see what this can do to our health. So that's what this section is about. So let's talk about the background radiation. Let's sit on this stool. I can see y'all. Okay. So the typical background for us in the United States, we would have natural sources and man-made sources here. So this cosmic radiation is mostly from the sun, but there are a few, I don't remember how many thousand years ago, there was a nearby supernova that exploded. So a star exploded, and that's not an insignificant amount of our exposure because it's hitting us with things like oxygen nuclei and stuff that are just blowing right through our atmosphere, through us, through the earth. These particles are going so fast, and it's kind of like a sonic boom. When a plane goes by, you hear this huge disruption in the air. These things do that, but with charge. They come flying through your body, and they'll leave a little shock wave of ionized particles. And so it's kind of hard to conceive that a whole oxygen nucleus, one, could be stripped of all of its electrons, and two, be traveling so fast that it just goes right through you. But it's not there's not a lot of it, or we'd all be dead. So, it's occasionally bad luck. You'll get hit by a cosmic ray that creates some ionized molecules in your body, and a few cells die, and your body processes them, and you go on your merry way. But that's the cosmic radiation. That's the products of the fusion reactions happening in stars, and we're closest to our sun, and so we get some of that. And then Earth, we have radioactive elements in the Earth, and we collect some of those and put them in bricks and mortar. We try to avoid the really strongly radioactive, so that's why bricks and mortar are less radioactive than natural rocks and so on. And then human tissues, there's some radioactive versions of potassium, carbon-14, and so on. So we get that just from our own tissues and from each other. And then from air, so argon or radon gas in the air, just in general, but also, what other radioactive substances might there be? That would be the most prevalent. So the natural sources would add up to about 126 millirem per year. And then from man-made things, if you've had X-rays, if you've had other kinds of radiotherapy, where they, like if you have cancer and they put in these radioactive seeds next to the cancer cells to destroy them. This would be the background of everybody from having that kind of therapy, like having that in existence, stray x-rays and things. From the nuclear power industry, again, this is averaged over the population, so very little exposure from nuclear power. So like if you live next to a nuclear power plant, you're not experiencing a huge increase in your radioactive doses. My mom used to always tell me, don't sit too close to the TV, right? And I guess in theory it could emit x-rays because you have an electron gun in there that's hitting a screen, a phosphorus screen, and those electrons could knock out some 1s electrons and have sort of electron-induced x-ray fluorescence. And so she was a little bit right, but it wasn't a strong source of radioactivity. And then we've gotten away from that because we don't have cathode ray tubes anymore. So that's pretty rare. So that's probably dropped to zero. And then radioactive fallout from all of the testing of nuclear weapons in the atmosphere back in the 50s and 60s. So that's being blasted around, and it's some of that potentially still in the atmosphere, and we may still have some radioactive exposure to that. So 67 millirem per year from human sources. So that adds up to 193 millirem per year. Millirem. So it's a small amount. If you live in a radon area, that can increase your dose by another 200 millirem per year. And so I say depending on where you live. So this morning before class, I went and found some maps. And this is how radon gas gets in your home, through cracks in the rock. If you have a water well and you don't have a sparger that sparges or aerates that water and drives the radon out, and you live in a radon affected area, then your water could have radon in it, and that's bad. You're in the shower and it's spraying, radon infused water in your face, and you're breathing it in a concentrated area. So this is, again, it's coming from the soil if you're in these areas. Like look where it's in the Midwest here. It's over in Pennsylvania in the Appalachian Mountains, and a little bit in the Rockies, and maybe a little bit up here in the Great Salt Lake Basin. So those are the real strongly impacted areas from radon gas. So this is from the CDC site, and they talk about about half the lung cancers come from radon. And it makes it seem like a double threat. If you're, I was reading this morning, if you're smoking and in a radon area, that somehow the smoking allows the radon to get stuck in your body better. And it makes sense if you're sucking through a tarry cigarette, that tar, when it sticks to your lungs, could help the radon stick, like entrap it. And so if you breathe it in and breathe it out, you got to just be unlucky that the radon decomposes or decays when it's in your lungs. So that's a small probability. But if you're smoking and you're entraining the radon and tar, then it's going to be a higher probability that it decays while it's in your lungs. Once radon decays, what does it do? It becomes polonium. And then polonium becomes lead. And then lead spits out a beta particle and becomes bismuth. And bismuth spits out a beta particle and becomes polonium again. And then polonium spits out an alpha particle and becomes lead. And it just keeps going until it reaches a super stable version of lead. So the first lead it hits from uranium through radon is not the most stable. It bounces back and forth a little. It's like a ball bouncing at the end. It beta decays a couple of times to get back to polonium, and then goes an alpha again back to lead. So you get a bunch of particles. Once the first radon decays in your lungs or in your body, then you have like 6 or 7 more exposures to alpha particles and beta particles. So that's where the lung cancer is coming from. And it's, again, you breathe it in, so it's in your lungs. That'd be the first place it could decay. And if it decays in your lungs, then you get irradiated 6 or 7 more times. Okay. Again, it's if you do live in these areas, like if you guys get a job up there, don't let this freak you out. It's like, I can't work in Michigan or whatever, or Iowa. No, you just put a radon monitor in your house, and you get it tested, and then you have ventilation. So there's ways to clear out that space so that you're in a well-ventilated area. So what happens with the radioactive decay? You'll learn this week's lab in the radioactivity lab that alpha particles can be stopped by a piece of paper, a single piece of paper. And so same with your dead skin. So the alpha particles are so strongly charged, as soon as they hit the first surface, they latch themselves on to something and steal 2 electrons and become helium. So an alpha particle turns into a helium atom, and helium atoms are not toxic or anything like that. So as long as you have some shielding, clothing, dead skin, any of those things can stop alpha particles. Beta particles will go through those substances and into the body. So they'll get into the dermis, the sub-skin fat layer, and then gamma rays will go right through the body. So external exposure, beta particles are worse, but internal exposure, alpha particles are worse because they ionize twice as much, right? And they probably are indicative of something that's going to be in an alpha decay sequence, right? So if you get an alpha particle in your body, it probably came from one of those elements on the uranium train, and it's going to go down to lead, and it's going to continue emitting other alpha particles. So that's why in the radioactive measurement, they were talking about doses in that lecture, and the Q factor for alpha particles internally is times 20. So if you have an alpha emitter and it's ingested, it sort of gives you 20 times the dose. So that's pretty bad. How do we describe dangerous radiation? Well, we use water as the benchmark. So if it can ionize water, we call it ionizing radiation. If it can't, then it's essentially safe. So electromagnetic waves, I mean, that's light. And it's typically the same as radiation. So we have to come up with a new name for nuclear radiation. And so we call it ionizing radiation, using that 1200 kilojoule per mole, the first ionization energy of water. This matches our physiology because we're mostly water. So if we ingest a substance and it can ionize water, then it can cause reactions in our body that we don't necessarily want. So here's the acute biological effect. So this would be an incident where you got irradiated or came in contact with a radioactive source, like this lab. You guys are going to be exposed to radioactivity this week in lab. Am I nervous putting you in contact with a radioactive substance? And I've done the math, and no, I'm not nervous. Okay, but radiation is the dose. Do not eat the sources this week. You would get. I think you would get with the smoke detector. If you ate that americium source out of that smoke detector, you might get above the 25 rem threshold when you multiply by 20, for inside the body. So would it kill you? No, but you would have a slight temporary decrease in white blood cell counts, and the long-term effects is it might cause cancer, right? Because it's in your body. I work in rems, but you might hear sieverts. Sieverts are a tenth of a rem. So let's see, is that right, millisieverts? 100 millirem. Yeah. So I just work in rem. So 0 to 25 rem, there's no detectable clinical effects. And so it looks like a threshold. Above that, you can detect the impact on the body. And remember, we talk about toxin being the dose. So if you keep your doses below this, the body can handle it. And we'll discuss what the body's doing in a minute. Then between 25 and 50 rem, we have a slight temporary decrease in white blood cell counts. And then 100 to 200, you can start to see nausea. You might hear people talk about radiation sickness. Okay, this is where we start detecting that radiation sickness. But really, it's happening below that, down to 25 rem. And then 500 or more, that's the expected death of half the population. So that's the LD50. If you get 500 rem, you have a 50-50 chance of dying from it. What would that be like? Well, it's going to attack some of your organs. And so you could probably survive if it didn't destroy any one of the organs. But if you have a whole organ destroyed and you can't get a transplant, then you're not going to live. So how do we deal with this? Well, this is the administrative limits that we have at power plants and also at Pantex, where I used to work. At Pantex, it was 0.1 rem per year, then you were removed from your duties. So like if I went down and worked in a radioactive area with special nuclear material, I wore a badge, a film badge. And every month I would we always come out of the radioactive area and we put our film badges on a board with a number, and they would come through and collect them and replace them with fresh badges. And then they would go get that film developed. And if it was more exposed, that meant you had a dose in that month. And so they would add up your total dose. So that's how they keep track of your exposure. That's for people who are just sort of in the radioactive area. Some people actually doing manipulations with radioactive objects might wear rings, dose rings. And so they'll probably get tested daily in terms of those operations because they're working with radioactive substances and they want to make sure that they keep track of their exposure. So they can pull them off of their duties before they get above this, or when they get above this administrative threshold. So let's say I went in there and something happened and everybody in the room got dosed. They would go measure our badges and they would say, sorry, Williams, you got above a 0.1 rem. So you're done for the year in working in that area. And so when the year resets, then I can go back down. And it keeps your doses at a low and manageable level for your body. So what's happening with these doses is that you're getting kind of like a burn, if you will. So let's take a side trip and talk about about nuclear power. And then we'll talk about the health and how your body interacts with it. Were y'all, let's see, I don't know how old you were when the Japanese, they had the earthquake, which caused a tsunami, which caused the nuclear power plants to shut down. And then there was an explosion. How old were you? Do you remember? No. Yeah. Did it freak you out? A little bit? Yeah. So what happened was they had an earthquake offshore, and I think it was a slip. It doesn't matter which one it was, but it created a tsunami. And so then this tsunami comes, and they had their electrical generators. It's an island nation, right? So they're not dumb, right? They had like this tower with their generator on it. So they got a nice little generator that generates power for the water pumps over here in this thing right there. So these are power cables. Okay. And this is a cooling pool, right? So this is a spent fuel pool. So when they have spent fuel, they pull it out and they set it in this pool on site for several months to let the shortest half-life radionuclides decay away. So it's super hot, like kill you if you get near it type hot, for several months to maybe a year or two. And so they let that thing cool down and calm down, and then they can manipulate it and get it out and take it and reprocess the fuel. Okay, so this is just a little hot pool, and they built this, I think it was something on the order of 5 meters high. And the tidal wave was like 5.5 meters. So it came in and shorted out their diesel generators, and they couldn't get them started again. So they couldn't circulate that water. That's what caused the explosion. It wasn't the nuclear part that blew up. It was the spent fuel pool. And what happened is it just boiled the water down to where the cladding on the so this water level dropped, and when it exposed the fuel right here at the top edge, that metal's not being cooled by water anymore, and so it's uranium oxide pellets, like a ceramic pellet surrounded by zirconium alloy, and it got super hot, and the water right at the edge was hot enough to just make water break into hydrogen and oxygen. So, right, the reverse reaction of hydrogen and oxygen making water, you can run that in reverse if you get hot enough, and it'll just break apart. So up here in this top area, you had a stoichiometric amount of H2 gas plus O2. And they knew it was just a matter of time before the top of this building was going to blow up. And so they had a picture, there's on video. It's a unbelievable explosion, it's so perfect that this rectangular roof just goes straight up. Okay, and that was it. It was a very calm explosion. It was just like pow, like a detonation, and this roof goes straight up in the air, and then it comes crashing down, and it's radioactive, and they got to clean it up. Okay, what had happened to the reactor, though, when the tsunami came through and the earthquake cracked some of these containment areas down here for the primary water loop. And so that's the long-term problem with this disaster, was that the primary water leaked out, and so we have some radioactive water in the groundwater. Okay. The reactors behaved perfectly in this earthquake. As soon as it detected an earthquake, the control rods dropped in and started shutting down the reaction. So it started absorbing those neutrons and calming the reaction down. So that safety system worked perfectly. The generator, they need a backup for their backups, so that was a problem that they discovered. And then the earthquake did damage the primary water loop, and it has a leak in it. So that what they do is they monitor where the radioactive water goes, and they drill wells and they suck it out. So it's called a pump and treat. They pump the water out, and they somehow sequester the radioactivity with like an ion exchange column, and then they pump the fresh water back in. So they're flushing the groundwater with these pumps to keep it from going out into the ocean and getting into the fish, which is the large source of food for the population. So that's what's going on with that. In terms of the media, this is, as I've gotten older, now I'm 54, okay, I've just gotten less and less impressed with the media. They seem to hype everything so badly that during this shutdown, they were trying to get the reactors to cool down and manage the crisis that was happening, and the media was just hyping this up, that these people were working in their own graves, like the control workers. They said, oh, radioactivity is so bad, these people are standing in their own graves, they're so heroic to continue to work even though they know they're dead. And it wasn't that situation at all. It says that only one female worker received 17 millisieverts, or 1.5 rem, which is above the limit of a 0.5 rem every 3 months. And so that's their administrative limit. So she burned herself up for the year, but did not go above the 25 rem threshold. That was the highest dose in the whole incident. And the media was telling us that these people were working in their graves. It was just not right. And anyway, I get really irritated. There were 201 people working at the Daiichi plant. The Daiichi had 645 people. Nobody went above 25 rem. 30 went over 10 rem. Okay. And then, and yet, because of the media hype after this, Germany decided to phase out all of its nuclear power, which was a knee-jerk reaction. So this is it's really important to not hype things up. This is just a comparison of the death toll per 1,000 terawatt hours, or 3.6 exajoules. So I said, well, what would be the deaths for 425 exajoules per year? So for nuclear, it would be 10,600 deaths per year if everything operated on the same average and the whole world ran on nuclear. And coal would be 11,800,000 deaths per year. So I'm a fan of nuclear, obviously. And natural gas, almost 500,000 deaths per year. Wind, 17,000. So even wind is more dangerous than nuclear. So anyway, there was some rubble that was extremely radioactive. That roof that blew off of the power plant, it had a lot of radioactivity in it. So they had to get there and clean that up. And you can't go over there with shovels when it's blasting you with 30 rem per hour. Yeah. So 25 rem is that that baseline for discovering that health effects. and this is 30 in an hour. So if you work a 10-hour day, you're almost at the 50% death limit, right? So you would get really sick if you were cleaning up that debris. So they brought in radio control forklifts and dump trucks, and so all the guys like me and my son who like the radio control stuff, we're like, sign me up. put the Oculus Rift on and go in there and start cleaning it up. So let's think about the health effects. So there's two theories. The threshold theory is what I would call the regular metabolic theory, that you get above a threshold and your body gets sick. You stay below that threshold and your body can handle it. The doses are not additive, and that hormesis, this is a side thing, proposes that small doses of radiation are actually helpful for culling weak cells. That piece is controversial, so you don't have to have that in terms of the typical metabolic understanding of the health effects of radiation. Then there's the linear no threshold theory, LNT theory. And this says all doses are detrimental no matter how small. And this is the real issue. Doses are additive. So it says that you've got a dose, throughout your whole life, all of those add up to eventually giving you a health effect. And this was really played up in the 50s or late 50s, early 60s to enact the atmospheric test ban treaty. So they said radiation is unique. We can't handle it. It's foreign to our bodies, and we're going to all die because they're testing these nuclear weapons in the atmosphere. Okay. And it was a great scare tactic, and it worked too well because now everybody's afraid of radioactivity. Okay. It did enact the atmospheric test ban, so the Russians and the United States and all our allies, we started testing our nuclear weapons below ground and in underground, wells and caves, so that we don't spread it all over the globe. So that's a good thing, but the scare tactic has continued to this day. Now, what does it mean to have doses be additive? If we were to apply additive doses to things like automobile exhaust, then someday you will go anoxic because of CO poisoning, right? You walk through the parking lot enough times, and eventually you're not going to have the ability to carry oxygen because you've got CO2 latched onto the iron in your hemoglobin, and down you go. But we know that's not the way the body works. Yes, you could get in a dose of CO, and then your body's going to eventually cull that out and produce more hemoglobin, and it's going to refresh its ability to carry oxygen. So same with swallowing wrong. You ever swallowed wrong? You get a little water in your lungs and you cough. Well, this is linear no threshold theory would say that's additive. So one of these days you're going to swallow wrong and drown. Right? Because you never were able to clear that water out of your lungs or absorb it through your lungs. And so this additive dose model is really not the way the body works. Okay. There are some things that do accumulate in the body, and we'll look at those in a second. So this is our Toxicology 101. The acute toxin is the dose. So we absorb, distribute, metabolize, and eliminate toxins. So absorption, most of this is ingestion, but you can get things through your skin and normal environmental inputs. So then it's distributed over the body. Now we can, like I said, ingestion of radioactive sources is bad because you absorb the dose very efficiently in your body. Keeping it outside the body, that's great. So we can limit our exposure by time, distance, and shielding. And that's how we keep the rate of our insult to our body at a minimum. And then elimination, if it is producing like a noble gas, like radon, breathing it out. If it's something that, like tritium, if it's hydrogen-based, you want to flush your body with water. You want to take a diuretic and drink lots of fluids, and so that you can eliminate that tritium. And you can test that by taking urine samples and sending it off for radioactive analysis. So you can follow radioactivity pretty well. So this is that normal toxicological treatment where you're measuring, say, biological effect of death. Well, then that LD50 is that 50% chance. It's the dose that gives the threshold of switching over to more probable death than less probable. And here are the biological half-lives of industrial substances. And when I said that your body will process most things and eliminate it, some of these substances like polychlorinated biphenyls, you see over here, right there, and cadmium. Cadmium, the half-life, and this is not radioactive half-life, this is the biological half-life. So if you are exposed to cadmium, it will latch onto the sulfur in your enzymes and so on, and it will stay in the body over 10 years. That's the half-life. So half of that dose will be gone after 10 years. So rule of thumb for being completely eliminated is 10 times the half-life. So 100 years to get rid of cadmium. So polychlorinated biphenyls are not much better. They stay in the body. It's just that they're inert. They stay in your fatty tissues. And that's the same with these PFAS compounds. It's really scary in the sense that they're showing up in our fatty tissues, but it's also not so scary in that they're very inert. So these carbon-fluorine bonds are very inert, but they approve these compounds to be used in cosmetics and perfumes and so on. And so we're spraying these things even in our faces and then breathing them in, and then they're getting accumulated in our body. They call them forever chemicals. Okay, but the toxin part of radioactivity is the light that it emits or the particles that it emits. And so it behaves more like a sunburn. So what's happening with radiation is that it's killing or damaging cells. So think about getting a sunburn. If you ever go out in the summer, you get sunburn, what happens? Your skin peels. Why is your skin peeling? It's because it's destroying those damaged skin cells and producing more skin cells underneath. And so then it's peeling off. It's like a whole body blister. Okay. And sometimes you can get a bad enough sunburn that it will blister. And that's a really bad one. But that's from UV light, same exact thing for radiation. If you were to ingest a lot of radioactive substance, like the Russians killed this journalist that wrote about them, and they didn't like what he wrote, so they put polonium on his fish and chips in Britain. And the guy ate it, and his stomach lining and his stomach, that whole organ was destroyed. Yeah. Pretty gruesome, yeah. But that's how you die of radiation. It wasn't the toxicity of the polonium, it was the burn he got on his stomach. You can look at that CNN special on what was it, HBO? I think it was HBO, on Chernobyl, and those guys that fought that disaster, they were just all burned up, and it wasn't so much their skin as their organs. Like if it irradiates your liver, then you could lose that whole organ, and then you can't even metabolize half the things you need to. So that's why we reduce our time in dealing with radioactivity. We keep our distance, and we put shielding between us. So in this week's lab, you're going to be in there. Don't put the stuff against your skin and hold it the whole time during lab. That's against this time, distance, and shielding. You always reduce your exposure as low as is reasonably achievable. We talked about radon gas. So the most dangerous isotope in this list is in terms of radiation exposure, maybe the shortest one, like iodine-131, but really it's strontium-90 in this list because it is in the same group as calcium, and it will get incorporated in the bones. So again, the time issue, if you were to ingest strontium, radioactive strontium, it would get absorbed into your bones. And so it's most dangerous for infants because they're generating bone. And so if we have strontium spread over farmland and cows eat that, it's in the milk, and they feed that to young children, it's going to be in their bones, and they're going to end up with leukemia. So strontium-90 is probably the worst one in terms of persistent effect on the body and the persistent ability to cause cancer. This medical breakthroughs, we use radiation for imaging, like thyroids and brain cancers and so on. And then this is where we get our radioisotopes in these research reactors. This is at the University of Dayton. And this you're looking at a nuclear reactor right down here. You see the kind of the blue light coming out of there? That's the radioactive effect of the particles coming out of that reactor faster than the speed of light in the medium. Basically, it's like a fluorescence effect. And you see all these tubes that go down there. You can take radioactive targets, put them in a Teflon tube, and just like the bank teller, you use air to throw it down in there and expose the heck out of it with neutrons or whatever, and then pull it back and do chemical analysis and extract the goodie. So they get moly-99, which turns into technetium-99, which we inject into patients with heart disease and image their heart and how the blood flow happens in the heart. So we use radioactive isotopes to image things in the body. And all of our biochemical pathways, Krebs cycle, the citric acid cycle, all of those were determined with radioactive tracers. So you put in sugar and see what comes out. You put in this substance and see what comes out, and you can follow those radioactive substances through all those reactions. All right, so that's the